Welcome to today's lecture. So, by the end of this first section, you will be able to learn the key steps for perceptron learning, including how to detect misclassified points and how to update the plane by adjusting its weights and bias values. I will also provide graphical interpretation of the perceptron learning rule and show you how the unified learning algorithm is derived. Finally, I will also introduce a hyperparameter called learning rate, which is a speed accuracy trade-off. So, in the last session, we have learned the computational modeling of the perceptron and we showed its superiority over the MP neuron in three aspects. In this session, we will concentrate on the last advantage of the perceptron, that is, its learning ability to update the weights and the threshold values automatically. I will first give you a high-level description of the main steps for perceptron learning process and then provide details for each step. Given a set of labeled data points, the goal of training a perceptron is to identify its weights and threshold values, such that these data points can be correctly classified by the perceptron. We have learned that a perceptron is a binary classifier. Thus, graphically, training the perceptron is to find the plane to separate the labeled data points into two groups, where the coefficients of the plane are determined by adjusting the weights and threshold value. Initially, we randomly chose the weights and the threshold value w, b to create a plane wx plus b is equal to 0. In two-dimensional case, the plane is a blue line. Above this line is the positive region shown in light blue color. Next, we are going to detect if there exists any misclassified node, that is, to check if any green points outside the blue region or any red points inside the blue region. In this example, we see that these green points are correctly classified as they are in the blue region, and all the red points are correctly classified as they are outside the blue region. There is only one green point outside the blue region, which is a misclassified point. For any misclassified point, we need to update the plane by adjusting the weights and the threshold value wb. After that, we need to recheck if there exists any misclassified points. In this example, we can see that all the green points are within the blue region and there is only one red point inside the region which is misclassified as green. Then we again update the plane to exclude this point from the blue region by adjusting the weights and threshold value and recheck the existence of any other misclassified node. In this case, there are no misclassified points. Therefore, we exit for loop and output the weights and threshold value for the final plane. This is the basic step for training the weights and the threshold values for the perceptron. Throughout the learning process, we see that there are two steps which are very important. One is how to detect if there exists any misclassified node. The other one is how to adjust the weights and the threshold value to update the plane. So, let's first look at the detection of misclassified points. But before detailing the detection method, let's first revisit some geometry. So, given a straight line in 2 dimensions or a plane in 3 dimensions, we can represent it in a vector form wx plus b is equal to 0. Here, w is a norm vector which is perpendicular to the plane. For example, given a straight line y is equal to minus 2x plus 2, to get its norm vector w, we first rearrange terms as 2x plus y minus 2 is equal to 0. Then we put x and y's coefficients 2 and 1 together, which produces the norm vector w. It is perpendicular to the line. If we set the vector x is equal to x, y, then b is equal to minus 2, then the straight line will take the form wx plus b is equal to 0. Another example is in 3-dimensional case, where the given equation 2x plus 3y plus 4z minus 1 is equal to 0 is a plane. We put x, y and z's coefficients together to make w is equal to 2, 3, 4. This is a norm vector perpendicular to the blue plane. If we set vector x, y, z and b is equal to -1, then the plane also takes the form wx plus b is equal to 0. Next, let's revisit the relationship between the dot product and the angle of two vectors. Given two vectors a and b, if the angle of a and b is 90 degree, then the dot product is 0. If their angle is less than 90 degree, their dot product is positive. Otherwise, if their angle is larger than 90 degree and less than 180 degree, their dot product is negative. These results indicate that we can use whether the dot product is positive, negative or 0 to evaluate whether the angle of two vectors is acute, obtuse or right, respectively. The correctness of the above results can be derived from the dot product definition, where a dot b is defined as magnitude of a dot magnitude of b cos of theta. Here theta is the angle between a and b. Since a and b are two non-zero vectors, their magnitude is always positive. Therefore, a dot b is positive, 0 or negative, depending on the cosine theta value. We can see that from the cosine graph that when theta is between 0 and 90 degree, cos of theta is positive. When theta is exactly 90 degree, the value of cos of theta is equal to 0. When theta varies from 90 degree to 180 degree, the value of cos of theta becomes negative. This validates our above results. Based on this mathematical knowledge, next I will introduce how to determine whether a given point is inside the positive blue region. Given a plane equation wx plus b is equal to 0, for ease of our presentation, we first assume b is equal to 0 and w and x are in 2 dimensions. So in this case, wx is equal to 0 is a straight line across 0 point. This positive blue region is above this line, in which any point x satisfies wx greater than equal to 0. Thus, if the given point v is inside the blue region, v must also satisfy wv greater than equal to 0. Otherwise, if v is outside the region, wv less than 0. In this example, v is inside the blue region. Thus, w dot v is non-negative. The non-negative dot product implies that the angle between w and v is less than or equal to 90 degrees. Using the above result, let's take an example. Given the line y is equal to minus 2x, the positive region is above this line, shown in light blue color. Given a point v is equal to 1, 3, to determine whether v is inside the blue region, we first rewrite the equation into standard form. We notice that x and y's coefficients are 2 and 1, which makes the normal vector w of this line. Since the given point of v is 1, 3, then we calculate their product to see if it is positive or negative. Since the result of this product is 5, which is positive, therefore v is inside the blue region. This is consistent with the fact that the angle between the vector w and v is less than 90 degree. We next consider the case when b is not 0. In this case, the line is not across the 0 point. Given a point v, to determine whether v is inside the blue region, we can use a similar approach. If v satisfies wv plus b greater than equal to 0, then v is inside the region, otherwise outside. However, in this case, we cannot simply use the angle between v and w to determine if v is inside the blue region. Even if the angle between v and w is less than 90 degrees, there are still chances that v may be outside the blue region, because the blue line is not across the 0 point. To address this problem, when the plane is not across the 0 point, we can use a high dimensional space to represent this plane to make the plane across the 0 point in higher dimension. To be more specific, we now introduce two transformations in mathematics. One is affine transformation and the other is a linear transformation. If the line wx plus b is equal to 0 is not across the 0 point, we call it affine transformation. Otherwise, the line is across the 0 point, which becomes wx is equal to 0, and we call it linear transformation. It is important to note that any affine transformation in n dimension can be converted to a linear transformation in n plus 1 dimension. We can see in the linear transformation the last element of the vector x is 1. We now replace this one element with another variable x underscore n plus 1, and we let x underscore n plus 1 is equal to 1. This equation denotes a plane, and the wx is equal to 0 denotes another plane. We notice that the intersection of these two planes in n plus 1 dimension is exactly the line in n dimension. Therefore, for binary classification problem, if the decision boundary wx plus b is equal to 0 is not across the 0 point in n dimension, we can convert it to a plane wx is equal to 0 that is across the 0 point in n plus 1 dimension. To explain this more clearly, let me take an example. So, given a data point v and a line in 2 dimension, we want to determine if v is above this line. Since this line is not across the 0 point, we cannot simply use the angle between vector v and w to determine if v is above the line. However, if we convert this line into 3 dimension, it will become a plane that is across the 0 point. Specifically, we can add an element of b into vector w and an element 1 into the vector x, and then the line takes the form wx is equal to 0 in 3 dimension. In the vector x, we replace the last element 1 with x3 and add another equation x3 is equal to 1. As a result, the red line in 2 dimension becomes the intersection of the two planes in 3 dimension. Now let's visualize these two planes in 3 dimension. The plane x3 is equal to 1 is shown in blue color, which is parallel to the plane spanned by x1 and x2. We can project the red line and the given point v onto this blue plane. wx is equal to 0 denotes another plane shown in red color, which is across the 0 point in 3 dimension. The norm vector of this red plane is denoted by w, which takes the value w1, w2, b. It is important to notice that in 2 dimension we use a red line for binary classification, and the red line may not cross the 0 point. When converting it into 3 dimensions, we can use this red plane for binary classification, and this red plane is across the 0 point in 3 dimension. From this example, we can clearly see that in the 2-dimensional blue plane, v is above the red line, and this is equivalent to the fact that in 3 dimension, v is below the red plane. When using the red plane in 3 dimension as a classifier, we can use the angle between its norm vector w and the data point v to determine if v is above the line. Based on the above discussion, we can use the expression wx is equal to 0 to represent a plane. Here, the vector w may contain both weights and the bias value. For an ideal classification, we expect all the green points are inside the blue region. That is, the angle between each data point vector v and w is less than 90 degree. Ideally, the red point v should be outside the blue region, satisfying the angle between w and the red v is larger than 90 degree. However, in this example, there is a misclassified point v5. Therefore, we are going to train the plane by adjusting its coefficient w. We next study how to update the plane by adjusting the weights and the bias values. To show the learning rules for Perceptron, let's first revisit two vector operations. Given two vectors a and b, their vector sum a plus b is obtained by connecting a's head to b's tail and drawing the vector from a's tail to b's head. This follows the parallelogram law. Similarly, AB is obtained by drawing the vector from b's head to a's head. Based on these two vector operations, now we see how to train the perceptron. In this example, we notice that the green point V5 is misclassified as red, which is outside the blue region, indicating that the angle between vector V5 and W is larger than 90 degrees. In this case, when a positive data point is misclassified as negative, we use the following rule to update W, that is, W new is equal to W old plus V. In this example, to update W, we add the current W and V5 together, which produces a new vector W in purple color. We then rotate the plane to make the line perpendicular to the purple vector. After rotation, we see that all the green points are inside the blue region. However, there is another red point V6 whose value is 0, that is misclassified as positive in the blue region. In this case, the angle between vector V6 and W is less than 90 degrees. To exclude V6 out of the blue region, we use the minus learning rule, that is, W new is equal to W old minus V. Then a new vector W is produced, shown in purple color. Based on this new vector, we rotate the line to make itself perpendicular to the purple vector. After update, we notice that all red points are outside of the region and all green points are inside. There are no points misclassified. Thus, the learning process is complete. So, based on the above example, let's now summarize the learning rules for Perceptron. Firstly, we initialize W at random to create a plane. When there exists any misclassified input V, the following loop begins. If V is positive but misclassified as negative, that is, the angle between the vector W and the V is larger than 90 degrees, then we use the plus learning rule. We add V to old W to get new W. Otherwise, if V is negative but misclassified as positive, that is, the angle between vector W and V is less than or equal to 90 degrees, then we use the minus learning rule. We subtract V from old W to get new W. The above loop continues till there is no misclassified points. It is important to note that the above learning process can be simplified further by merging the above two cases together. This is because in one case, positive V can be written as plus 1 into V. Here, 1 can be regarded as the actual value 1 minus the predicted value 0. Similarly, in case 2, minus V can be written as plus of minus 1 into V. Here, minus 1 can be regarded as the actual value 0 minus the predicted value 1. In both cases, we notice that these parts are the actual value of the data points, whereas these parts are the predicted values of the data points from the perceptron. Therefore, these two cases can be merged in a unified manner as actual value minus predicted value. Consequently, we can simply use a single equation to describe the aforementioned two cases. To be precise, we use y of v to denote the actual value of v and y hat of v to denote its predicted value. Here, the values yv and y hat v are 0 or 1. Then the learning rule can be described as follows. W new is equal to W old plus the difference between actual and predicted values multiplied by v. In practice, we often put a small positive factor alpha in front of the difference. Here, alpha is called the learning rate, whose value is user specified, which is between 0 and 1. Alpha is a configurable hyperparameter, and we introduce the alpha because it determines the step size at each iteration in the training, which is a speed accuracy trade-off. If alpha is set to be smaller, it will take more iterations, leading to slower convergence rate. In contrast, larger alpha will result in rapid changes that may make the learning jump over the optimal solution. Here is an example which shows the effect of different learning rate alpha. When alpha is set to 1, the step size becomes so large that it may make the learning jump over the optimal solution. Therefore, the blue region will rotate too much and include even the red point. In comparison, when the alpha is set to 0.1, this will make the blue region rotate mildly by taking small steps so that it would not include the red point. So next we will move on and see the multilayer perceptron. So now let's move ahead, and now we are going to study multilayer perceptron, MLP. So we kick off with a simple well-known example of an XOR gate and show that XOR cannot be emulated by a single layer perceptron. Then we introduce multi-layer perceptron to address this issue. Specifically, upon completion of this section, you will be able to learn the basic notion of linear separability and theoretical reason why XOR is not linearly separable. Then I will introduce two treatments to address the XOR problem. One approach is to replace the threshold function of a single layer perceptron. The other approach is to increase the number of layers using multi-layer perceptron. You need to know the pros and cons of each method. More importantly, you need to understand the representation of XOR using multi-layer perceptron is not unique. There are many alternative ways based on different decomposition of the decision boundaries. Finally, we will learn how to use multi-layer perceptron composition to represent complex decision boundaries, which highlight the great potential to extend multi-layer perceptron for image recognition. So before introducing the MLP perceptron model, let's first look at the Venn diagrams of the logic gates, which is an effective way of visualizing logical relations amongst a collection of different sets. Given two sets x1 and x2, the overlapping region in yellow included in both x1 and x2 represents the AND gate, which is intersection of x1 and x2. The combined region of x1 and x2 represents the OR gate, which is the union of x1 and x2. The complement of x is the universe set, which represents a NOT gate. A NAND gate is not AND gate, whose output is 0 only if all the inputs are 1s. The output of the NAND gate is complement to that of the AND gate. Thus, the Venn diagram of the NAND gate is the complement of the intersection of x1 and x2 in the universe set. An XOR gate implements an exclusive OR. Here, exclusive means XOR must contain x1 or x2, but not both, which implies that the output of the XOR gate is true if one and only one of the inputs is true. Thus, the Venn diagram of the XOR gate is the union of x1 and x2 minus their intersection. The last gate is imply. The only situation in which an imply gate output is forced is where the antecedent x1 is true but the consequent x2 is false. In all other cases, the imply gate output is 1. Thus, the Venn diagram of the imply gate is the complement of the orange region in the universe set. Utilizing Venn diagrams, it is easy to show that any derived gate such as NAND and XOR can be rewritten using only the basic gates AND, OR and NOT. In particular, the following two expressions are worth noticing, which will be useful to our further discussion. The first expression is x1 NAND x2, which is equal to NOT of x1 and x2. Based on the Venn diagram of the NAND gate, this expression follows immediately from the fact that the true yellow region of the NAND gate is equal to the universe set minus intersection of x1 and x2. The second expression is about XOR, which can be expressed in terms of OR, AND and NAND. So, to validate this expression, we can see that from its Venn diagram that XOR equals the union of x1 and x2 minus their intersection. Based on the set theory, we know that for two sets A and B, A minus B can be expressed as A intersects the complement of B. In our expression, D is the intersection of x1 and x2, that is the AND gate. Thus, the complement of B becomes the NAND gate. Here, the set A is the OR gate. Therefore, the above expression for XOR gate is immediate. Next, let's look at the linear separability of a logic gate. Linear separability is an important concept in neural networks. The idea is to check whether we can separate data points in an n-dimensional space using only n-1 dimensions. For example, a two-input logical gate is said to be linearly separable if there exists a line separating the two types of data points in two dimensions. The AND gate is linearly separable because when we depict its four training data points into two dimensions, we can separate them using a line x1 plus x2 is equal to 1.5, such that the point with the green label is in one half blue space and the 3 points with red labels are in the other half space. Similarly, an OR gate is also linearly separable because we can separate its training data points using a line x1 plus x2 is equal to 0.5, such that the 3 data points with green labels are in half blue space and one red point is in the other half space. However, not all the logic gates are linearly separable. One counterexample is the XOR gate. We can see that there does not exist a single line that splits the 4 data points into two categories, such that the 2 green points are in one half space and the 2 red points are in the other half space. Therefore, we can say that XOR is linearly inseparable. For linear separable logic gates, we train a perceptron to mimic it and apply the perceptron learning rules to determine the weights and bias of the separate line. For example, for the AND gate, we can find the blue region is x1 plus x2 greater than equal to 1.5. By comparing this inequality with the standard form of the perceptron decision boundary, we can get the coefficients w1, w2 and b, which is 1, 1 and minus 1.5 respectively. Therefore, the perceptron for the AND gate is the following. Similarly, we can train a single layer perceptron to mimic the OR gate. The weights of the OR gate perceptron are all ones, the same as the weights of the AND gate. The only difference is the bias value, which is minus 0.5. This is because the separate line of the OR gate is x1 plus x2 greater than equal to 0.5. Since both AND and OR gates can be emulated by a single layer perceptron, what about the XOR gate? Unfortunately, Minsky and Papert in 1969 theoretically proved it is impossible to use a single layer perceptron to represent the XOR gate. This result is consistent with the fact that graphically we cannot use a single line to correctly classify the 4 data points of the XOR gate into two categories. To theoretically prove XOR cannot be emulated by a single layer perceptron, let's take a look at its truth table, row by row. In the first row, the output y is 0, meaning that the neuron does not fire when x1 and x2 are zeros. Thus, you substitute x1 is equal to x2 is equal to 0 into this orange branch to get the following inequality. In the second row, the output y is 1, implying that the neuron will fire when x1 and x2 are 0 and 1 respectively. Plugging these values into the orange branch produces this inequality. Similarly, for the third and fourth rows, we can put the x1 and x2 values into the corresponding inequality. Consequently, we can get the following 4 inequalities, which makes a system of inequalities. Next, we are ready to check the existence of w1, w2 and b for the 4 inequalities. We simplify these inequalities and get the following. So from the results, we can see that the second inequality implies w2 plus b is non-negative. Substituting this result into the third inequality, we get w1 is negative. Combining this result with the first inequality, we see that both b and w are negative. Thus, there is w1 plus b is also negative, which contradicts the last inequality. Since these 4 inequalities are contradictory to each other, there does not exist such solution to w1, w2 and b. This implies that XOR cannot be represented by a single layer perceptron. To address this issue, there are 2 treatments. The first method is to replace the existing threshold function of the perceptron with a more powerful function. This method would make the existing activation function more complicated, but it can guarantee that only the single layer structure of the neural net is used for XOR representation. The second method is to increase the number of layers in the neural network. This method would increase the number of units and the depth of the neural net, but can guarantee that the activation function of each unit is still a simple threshold function. So let's first look at the method 1. Before replacing the threshold function, let's first study why it works well for the OR gate. These are the 4 data points and the decision boundary for the OR gate in 2 dimensions. In 3 dimensions, we can see that the 3 green points labeled as 1 are mapped onto the upper plane y is equal to 1. When the shape of the hyperplane in 3 dimensions is projected onto 2 dimensions, it looks like a step ladder, which is a Heaviside function jumping at the point 0.5. Note that the green upper plane in 3 dimensions is the result of elevating the blue region in 2 dimensions. We can translate this Heaviside function left 0.5 unit by adding a bias value minus 0.5 to the perceptron to make the threshold function 0-centered. Now let's apply the similar idea to the XOR gate. For XOR representation, the blue region in 2 dimensions becomes band lines. Unlike the OR gate, that needs to elevate half the space in 3 dimensions. In the XOR gate, we just need to elevate the blue band area such that the only 2 green points are mapped until the upper plane in 3 dimensions. When the shape of this hyperplane in 3 dimensions is projected onto 2 dimensions, it looks like a piecewise function whose value is 1 when x is between 0.5 and 1.5 and a 0 otherwise. The single layer neuron with this piecewise function can mimic the XOR gate. It is worth mentioning that the central idea of method 1 is to replace a simple threshold function with a more complicated piecewise function. This method has the advantage of reducing the number of nodes in the neural net but increases the computational burden for each node due to its growing complexity of the activation function, and the learning rules for the user-defined piecewise function are unclear as well. Moreover, in neural computing, our basic philosophy is to approximate a complicated function by decomposing it into number of simple functions which may contradict the main idea of method 1. Thus, this approach is not practically useful. The second method for XOR representation is to increase the number of layers and nodes in the neural net while keeping the threshold function for each node. So, when the number of layers for perceptron is larger than 1, we call this neural net a multi-layer perceptron. To mimic XOR with multi-layer perceptron, our basic idea is to convert the blue region into composition of several half spaces, such that each half space can be represented by a single perceptron. In this XOR example, we can observe the blue region is a band between 2 lines, which is the intersection of 2 half spaces. The first half space is the region represented by x1 plus x2 greater than equal to 0.5. This region is the decision boundary of the OR gate. The other half space is the region x1 plus x2 less than equal to 1.5. This region is the decision boundary of the NAND gate. The intersection of the OR and NAND gate makes the XOR gate. This relation is consistent with our previous expression of XOR depicted as Venn diagram. This is the Venn diagram of XOR, which is equal to the OR gate intersecting the NAND gate. Now let's first take a look at the OR gate with decision boundary. So it can be written as x1 plus x2 minus 0.5 greater than equal to 0. Comparing this with the standard form, we can get the weights and bias, which is a triple 1, 1, minus 0.5. This corresponds to the following perceptron for the OR gate. Similarly, the decision boundary for the NAND gate is minus x1 minus x2 plus 1.5 greater than equal to 0. Comparing this with the standard form, the weights and bias of the NAND gate is a triple minus 1, 1.5. This produces the following perceptron for the NAND gate. We see that both perceptrons have the same inputs x1 and x2. Thus, we can merge them into this neural net whose outputs are y1 and y2. Here y1 is the output of the OR gate and y2 is the output of the NAND gate. the intersection of y1 and y2 is the output y for XOR gate. The intersection can be expressed as an AND gate. From the previous session, we learned that the row hash diagram of y1 and y2 is the following, whose threshold is 2. This is equivalent to the following perceptron representation, whose bias value is -2 and all the weights are 1s. Therefore, let's merge this AND perceptron with the previous neural net, which produces the following result. This is the multi-layered perceptron which emulates the XOR gate. So, this solution to the XOR gate is provided by Minsky and Papert, who added a hidden layer to make two-layer neural network with 3 perceptron units. This unit represents the OR gate, this one is the NAND gate, and this one is the AND gate. It is important to note that this solution is not unique. There are many other multilayer perceptrons with different weights and bias that can address the XOR problem. For example, if the first unit represents an upper left half space and the second unit denotes a lower right half space, then their union makes the blue region, which can separate green points from the red ones. Therefore, in this situation, the third unit is the OR gate, corresponding to the union operator. Alternatively, we can also construct a line with a steep slope to represent the upper right half space and another line with a gentle slope to represent the lower left half space. The intersection of these two regions can correctly classify the green points as well. A variety of ways to solve the XOR problem indicate that a multi-layer perceptron can represent the decision boundary whose region is a polygon. To be specific, given an n-sided polygon, we can construct a multi-layer perceptron with n perceptron units representing the n sides of the polygon respectively, in combination of AND and OR gates for assembling these half spaces together to make a polygon region. For example, to represent the following positive green region whose boundary is a quadrilateral, we can construct a multi-layer perceptron with 4 perceptron units denoting 4 sides of the quadrilateral respectively. For example, this side implies the following perceptron to denote this half space. This side implies this perceptron, and this side corresponds to this perceptron. The last side is associated with this perceptron. Then we combine these 4 perceptron units together with an AND gate, which produces the intersection of these 4 half spaces, that is the green region. Thus, the multi-layer perceptron is the representation for the positive green region. The above example indicates that the perceptron can represent any polygon region through the composition of the perceptron units. Consequently, we can use the multi-layer perceptron to represent the complex decision boundaries. For example, an athlete-like shape. In this representation, the multi-layer perceptron is structured as follows. We have 2 inputs, x1 and x2, denoting the 2-dimensional data points on a plane. We first depict the head of the athlete, which has 4 sides, corresponding to the 4 perceptrons combined by an AND gate. Then the purple arm of the athlete is a 5-sided polygon, which corresponds to the 5 perceptron units intersected by the AND gate. Similarly, we can depict the blue arm, red leg, and the orange leg of the athlete respectively. After each component is depicted, we use an OR gate to combine them together, which yields an athlete-shaped region. In this way, the multi-layer perceptron can help recognize an athlete image. Interestingly, apart from an athlete image, applying the similar ideas in a fine-grained fashion, multi-layer perceptron can also recognize other complicated images such as animals, digital letters, and handwritten numbers. So with this, we conclude our session on multi-layer perceptrons. Now we move on to our Jupyter Notebook session. In this notebook, we will be exploring how to use Keras to build our neural network to predict if house prices are above or below the median value. In particular, we will go through the whole deep learning pipeline from exploring and processing the data to building and training our neural network. We will also have a look at visualizing the loss and accuracy and finally we'll add regularization to our neural network. In just a few minutes from now, you will have coded your own neural network just as a deep learning practitioner would have. The dataset that we are going to use today is adapted from Zillow's home value prediction Kaggle competition data. We've reduced the number of input features and changed the task into predicting whether the house price is above or below the median value. So we will start by exploring and processing the data. Before we code any algorithm, the first thing that we need to do is put our data into a format that the algorithm will want. In particular, we need to read in the CSV file and convert them into arrays. Arrays are a data format that our algorithm can process. Then we split our data into input features, which we call X, and the labels, which we call Y. Then we move on to scaling the data. We call this process normalization. We do this so that the input features have similar orders of magnitude. Then we move on to splitting our data set into the training set, validation set, and test set. So coming here to cell 1, we will first import pandas as PD, and then in cell 2 we will read the CSV file, and this line of code means that we will just read the CSV file houseprice.data.csv and store it in the variable df. Now if you want to find out what the df is, we simply type the variable over here and we run the cell. So here you can explore the data a little bit. We can see that in our input features we have 10 columns. So we have the lot area, we have overall quality, we have overall condition, total basement area, number of full bathrooms, number of half bathrooms, total number of rooms above ground, number of bedrooms above ground, number of fireplaces, garage area, and etc. At last, we have our column. We have this feature that we would like to predict. Is the house price above the median or not? So we have 1 for yes and 0 for no. Now moving on to cell 4. Now that we've seen what our data looks like, we want to convert it into arrays for our machine to process. So we do df.values. Now to see what's inside this variable dataset, we just print it. So this is how our arrays look. So you can see that our data is stored in a two-dimensional array format. Coming to cell 6, we now split our dataset into input features X and the feature we wish to predict, that is Y. To do that split, we simply first assign the 10 columns to our array to a variable called X and the last column of our array to a variable called Y. Now let me explain what's inside the square brackets here. Everything before the comma refers to the rows of the arrays and everything after the comma refers to the column of the arrays. Since we are not splitting up the rows, we put colon before the comma. This means that we need to consider all the rows in the dataset and put it in X. Then we want to extract out the first 10 columns, and so the 0:10 after the comma means that we take columns 0 to 9 and put it in X, but we don't include the 10th column. Our columns start from index 0, so the first 10 columns are really columns 0 to 9. We then assign the last column of our array to Y. So now that we have split our dataset into input features X and the label we want to predict Y, the next step is to process our data to make sure the scale of the input features are similar. Right now, features such as lot area are in the order of magnitude of thousands, and a score of overall quality is ranged from 1 to 10. Similarly, the number of fireplaces tends to be 0, 1 or 2, and this makes it difficult for the initialization of the neural network, which causes some practical problems. Now one way to scale the data is use an existing package from scikit-learn. So coming to cell 7, we will import pre-processing from sklearn. Then in cell 8, we will use a function called the min-max scaler. This function scales the dataset so that all the input features lie between 0 and 1, including both 0 and 1. Note that we choose 0 and 1 intentionally to aid in the training of our neural network. We won't go into the theory behind this for now. So our scale dataset is stored in the array x_scale. In 9, if you wish to see what x scale looks like, we simply run this cell. Now we are down to our last step in processing the data, which is to split our dataset into a training set, validation set and a test set. We will use the code from scikit-learn called train test split, which, as the name suggests, splits our data into a training and test set. In cell 10, we will first need to import the code, so we import train test split from model selection. Then in cell 11, this code tells scikit-learn that your val and test size will be 30% of the overall dataset. The code will store the split data into the first 4 variables on the left of the equal sign, as the variable name suggests. Unfortunately, this function helps us to split the dataset only in 2 parts. In cell 12, since we want a separate validation set and test set, we use the same function again to do the split on val and test data. The code above will split the val and test size equally to the validation set and test set. In summary now, we will have a total of 6 variables for our datasets that we'll use. We have the xtrain that has 10 input features and 70% of the full dataset. We have xvalidation which has 10 input features and 15% of the full dataset. Then we have the xtest which has 10 input features and 15% of the full dataset. Then we have the labels that are divided into ytrain, yval and ytest, and they are divided into 70%, 15% and 15% respectively. So coming to cell 13, if you now want to see how the shapes of these arrays look like and what dimensions they are, we simply run this line of code. As you can see, the training set has 1022 data points, while the validation and test set have 219 and 219 data points each. The x variables have 10 input features, while the y variables have only one feature to predict. And so now, finally, our data is ready. Normally, we know that machine learning consists of 2 steps. The first step is to specify a template or an architecture, and the second step is to find the best numbers from the data to fill into that template. Our code from here on will follow these 2 steps. In the first step, we'll set up the architecture. So the first thing that we have to do is we set up the architecture of the neural network. Let's first think about what kind of neural network architecture we want. So suppose we want this kind of a neural network that you see in this image. Here we have hidden layer 1, hidden layer 2, and we have the output layer. In hidden layer 1, we want 32 neurons of ReLU activation. In hidden layer 2, we want 32 neurons of ReLU activation also. And finally, in the output layer, we want 1 neuron of sigmoid activation. So we need to first describe this architecture to Keras. We will be using the sequential model, which means that we will merely need to describe the layers above in the sequence. So coming to cell 14, first let's import our TensorFlow package. Then in cell 15, we will build our neural network layer by layer. In the first layer, we have a dense layer of 32 neurons, and it will have an activation type of ReLU. The input shape is 10, since we have 10 input features. Notice that it is a dense layer, and dense refers to a fully connected layer, which is what we will be using. Our second layer is also a dense layer with 32 neurons and a ReLU activation. Note that we do not have to describe the input shape here, since Keras can infer the input from the output of our first layer. Our third layer is a dense layer with 1 neuron, and it's having an activation of sigmoid type. And just like that, we have written our model architecture. The second step is filling this architecture with the best numbers. Now that we've got our architecture specified, we need to find the best numbers for it. Before we start training, we have to configure our model. We configure our model by telling it which algorithm we want to use for optimization, and we tell it what loss function to use. We also specify what other metrics you want to track apart from the loss function. So, configuring the model with these settings requires us to call the function model.compile. In cell 16, we put the following settings inside the brackets after model.compile. So, for our optimizer, we have stochastic gradient descent, which is SGD, and we've seen this before also. Our loss is binary cross entropy. The loss function for outputs that take the values 1 or 0 is called binary cross entropy. Lastly, we want to track accuracy on top of the loss function. Now once we've run this cell, we are now ready to train. Training on the data is pretty straightforward and requires us to write one line of code in cell 17. The function is called fit, as we are fitting the parameters to the data. So we have to specify what data we are training on. So we will be training on xtrain and ytrain. Then we specify the size of our mini batch and how long we want to train it for, and that will be the number of epochs. So we have provided a batch size of 32 and we will be training for 100 epochs. Lastly, we also specify what our validation data is so that the model will tell us how we are doing on the validation data at each point. This function will output a history which we will save under the variable hist. We'll use this variable a little later when we get to the visualization part. You can now see that the model has trained, and by looking at the numbers, you should be able to see that the loss decreases and the accuracy increases over time. At this point, you can experiment with the hyperparameters and neural network architecture. Run the cells again to see how your training has changed when you tweak your hyperparameters. Now coming to cell 18, once you are happy with your final model, we can evaluate it on the test set. To find the accuracy on our test set, we run this piece of code. The reason why we have used the index 1 after the model.evaluate function is because the function returns the loss as the first element and the accuracy as the second element. To only output the accuracy, simply access the second element, which is indexed by 1. Since the first element starts its indexing from 0. Now due to the randomness in how we split the dataset as well as the initialization of our weights, the numbers and graphs will differ slightly each time we run our notebook. Nevertheless, you should get a test accuracy somewhere between 80% to 95% if you followed the architecture that we have specified over here. Next, we talk about overfitting and regularization techniques. How do we know if our model is currently overfitting? What we might want to do is plot the training loss and the validation loss over the number of epochs that have passed. So coming to cell 19, we first import the package matplotlib. We will be using this package to plot our curves. Then in cell 20, we want to visualize the training loss and validation loss. To do that, we plot the history of loss and validation loss. In cell 21, we can run the similar kind of code to plot our training accuracy and validation accuracy. Since the improvements in our model to the training set looks somewhat matched up to the improvements of the validation set, it doesn't seem like overfitting is a huge problem in our model. Now, for the sake of introducing regularization to our neural network, let's formulate a neural network that will badly overfit on our training set, and we'll call this model number 2. So in cell 22, you can see that we've made a much larger model with additional layers and 1000 neurons per layer, and we've used the Adam optimizer. Now Adam is one of the most common optimizers that we use, which adds some tweaks to stochastic gradient descent such that it reaches the lower loss function faster. If we run this code and we plot the graphs in cell number 23 using the similar code as above, we get a plot like this. Now this is a clear sign of overfitting. The training loss is decreasing, but the validation loss is way above the training loss and it increases. Now the inflection point here is about epoch number 20. After this, we can see a clear divergence between training loss and validation loss. Now in cell number 24, we plot the accuracy using this code. Here we can see a clear divergence between training and validation accuracy as well. Now let's try out some of our strategies to reduce the overfitting. So here we'll incorporate L2 regularization and dropout. The reason we don't add early stopping here is because after we've used the first two strategies, the validation loss doesn't take the U shape we see above, and so stopping early will not be as effective. Therefore, in cell 25, we specify our third model like this. To add L2 regularization, notice that we've added a bit of extra code in each of our dense layers, like tf.keras.regularizers L2, and in the brackets we have passed 0.01. Now this tells Keras to include the squared values of those parameters in our overall loss function and weigh them by 0.01 in the loss function. Then we have also used dropout. To add dropout, we added a new layer and we set the dropout to 0.3. This means that the neurons in the previous layer have a probability of 0.3 in dropping out during training. Now coming to cell 26, let's compile it and run it with the same parameters as our model 2. And now in cell 27, let's plot the loss and accuracy graphs. You will notice that the loss is a lot higher at the start, and that's because we've changed our loss function. To plot such that the window is zoomed in between 0 and 1.2, we add an additional line of code of plot.ylim. So this is what our loss graph looks like. You can see that the validation loss is much more closely matching our training loss. Now in cell 28, we'll plot the accuracy with similar code snippet used before. And we get a plot like this. Compared to our model in model 2, we've reduced overfitting substantially, and that's how we apply regularization techniques to reduce overfitting to the training set. So we've been through a lot, but we haven't written too many lines of code. So building and training our neural network has only taken about 4 to 5 lines of code, and experimenting with different model architectures is just a matter of simply swapping in different layers or changing different hyperparameters. Keras has indeed made it a lot more easier to build our neural networks. So with this, we conclude our lecture.